So tomorrow, two of the topics that you're going to see are going to be 4.1 and 4.2. So we're going to go again and look in-depthly at mean value and rules. So what I did is I kind of gave you a history of Rolle's theorem, just trying to give you an idea of how this came about in calc. So imagine 2 points on the x-axis. And basically, any 2 points, as long as they are at the same height, are going to be able to create a function that is differentiable. So you can draw any sort of lines between them as long as it starts and ends at those 2 points on that x-axis. Since our functions are differentiable, they're also continuous, and their graphs cannot have any holes or breaks. So what it means is that their derivatives are defined everywhere, and their graphs have no corners or vertical tangents. These graphs of all these functions have one common property, which is that f prime of c must equal 0 for some value of c. So basically what it's saying is that there is going to be a tangent line that is horizontal at some point, as long as your starting and end points are at the same height. So basically it's guaranteeing that you have a min or a max between those 2 points. That's what Rolle's theorem guarantees you, that there is a min or a max between those 2 endpoints. So Rolle's theorem has 3 hypotheses that lead to a conclusion. So basically, if it's continuous on a closed interval, differentiable on an open interval, and the beginning and the end are at the same height, then there is at least one point C in the open interval AB where f prime of c will equal 0. So what's in yellow is actually not on your papers. So Rolle's theorem, again, it concludes that there is at least one point C in the open interval AB where f prime of c equals 0, which basically means that the derivative has a tangent slope of 0. So the question could be posed, is there a value on this function where the slope of the tangent line is 0? Or is there a value on this function where there's a slope of 0? So the question's not going to come out directly and ask you to use Rolle's theorem. It's going to ask you about the tangent line having a slope of 0. And then you have to be able to say, oh, it's closed, it's differentiable, it starts and ends at the same point. So yeah, I can use Rolle's theorem and find that. So, in example 1, and I know we kind of did this yesterday. I know, I didn't fix them. That f of x is x cubed minus 6x squared plus 9x minus 2 satisfies the hypotheses of Rolle's theorem on the closed interval 0, 3, and find the value of c which the theorem says exists. So basically what we want to do is find f prime of x, which is 3x squared minus 12x plus 9. Maybe you take out the GCF of 3, giving 3x squared minus 4x plus 3. And it's very easy to say that Rolle's theorem's 3 hypotheses are true because number 1 is that f is continuous. Well, any polynomial function is continuous. So a cubic function is continuous. So this is continuous. 2, f is differentiable because once again, it's a polynomial. So since there's no division, no square roots, nothing messy, of course it's going to be differentiable. Also, the hardest theorem piece to prove is number 3, because I need to prove that f of 3 equals f of 0. F of 0 is always easy, because it's always the last number there at the end. So you get your -2. Now for 3, you have 3 cubed, which is 27. And then you have 3 squared, which is 9 times 6, so you get -54. Then 9 times 3 is another 27. And then -2. Well, 27 and 27 give 54, so 54 minus 54 all cancels. So we do in fact see that 3 and 0 both equal -2. So the 3 hypotheses check out. So that means that in conclusion, I can guarantee there is a value for C such that f prime of C equals 0, which means that 3 times C squared minus 4C plus 3 equals 0. So I can factor. So I have -3 and -1. And I see that when C is 3 and that when C is 1, the slope of the derivative, or the slope of the tangent line, will be 0. So what that means is that if I'm graphing this, 3 and 1 have to be mins or maxes on that original. Because the only time you're going to get a slope of 0 on your tangent is at a min or a max. So again, these C's are critical points or extrema, whatever you want to call them. But they are acting as critical points. So the mean value theorem is an extension or a variation, so to speak, of Rolle's theorem. So geometrically, you can take Rolle's theorem and tilt it, and that would give you the mean value theorem. And the reason for that is because the mean value theorem does not have that same hypothesis where f of A has to equal f of B. So what you're doing is you're taking that straight line f of A and f of B, and you're basically just putting them at a different angle. And that's the application behind mean value theorem. So both theorems conclude with a number C, where the slope of the tangent to f at x equals C is the same as the slope of the line connecting the two ends of the graphs. The only difference is that the slope in Rolle's theorem is always 0, and the slope in mean value theorem is constantly changing. So you're still setting derivatives equal to slopes, you're just setting them equal to different slopes. So again, there is a difference, but it's very, very minimal. So proving the mean value theorem is helpful, so to speak, because I think it really helps to connect what we're doing. So looking at the graph, let's talk about what we know. Is it fair to say that this line right here, g of x, is a linear function? Like, you believe that g of x is linear. It's going in a straight line. So the function g of x is linear. and the function meets with f of x at the endpoints. So it's also fair to say that g of a is equal to f of a, and g of b is equal to f of b, right? Because you agree that these two graphs meet here and here. So it's fair to say that g of a equals f of a, and g of b equals f of b. And let's go back to old school rise over run. Slope is y2 minus y1. So my y2 would be f of b, where my y1 is f of a. So it's fair to say that the slope of g is f of b minus f of a all over b minus a. Yeah, which would represent the slope of the secant. And isn't it also fair to think that the derivative of a linear function, think of any linear function you ever had. So if I told you y equals 2x minus 5, what's its derivative? 2, right? Because the constant goes to 0, derivative of 2x is 2. But if I told you y equals 10x plus 10, okay? So what are you noticing about this derivative of a linear function? It's a constant, and that constant is always the slope of the line. Yeah, see, that's what I was trying to get you to realize. Oh, 2x minus 5 is 2. 10x plus 10 is 10. Like negative x plus 2 would be negative 1. So the slope of a linear function is also the constant which represents the derivative of that linear function. So g prime of x is the slope of g of x. So the derivative for g prime of x is always, it's going to be a constant, yes, but that constant is going to be the slope of the linear function. So when you're talking about the mean value theorem, if you think about it, you immediately recognize this as the slope of the secant. Well, the slope of the secant line's derivative is its slope. So this is kind of like saying, all right, this here represents the linear function g of x, and this represents its slope, and this also represents the constant for its derivative.
So g prime of x is just that.
That's it. Because think about any linear function's derivative. It's just going to be, because this is ultimately going to represent some number. We just don't know the number. And knowing the number isn't really important.
So then if you write the equation, you can just use that as the slope and then use one of those points. That's how I was getting that, but then like I didn't know what to do from there.
So, and that's okay. Let's talk about the next piece of the problem. The next thing that we want to talk about is writing that equation for g of x. So it's fair to say that g of x minus, remember you subtract a point on your line. So you could use a, f of a, or you could use b, f of b. But it would be g of x minus the y value, which would be f of a, equals, exactly, that long slope, times x. Yep. So that gives me, well, all you have to do now to isolate g of x is just add f of a.
Well, yeah, but
yeah, the h of x is a little bit trickier to think about, and I tried to give you like the hint to write the equation of h of x as the vertical distance from f to g. So, but you can generalize it. So if you think about h of x, this right here would be f of, and we could call it C1, right? And this right here would be g of C1, because this C value would always be the same on the horizontal aspect. So like if this was C1, h of x would be f of C1, because that would be the y, that would give you the y height, minus g of C1. And then even if I move h of x over here, and I call this C2, isn't it always going to be f of C2 minus g of C2 now? So it's fair to generalize that h of x as a function will be f of x minus g of x, always. Because f of x is always higher than g of x, so the distance between them is always going to be how much higher is f than g. Okay, so h of x is always f of x minus g of x, and we could say or show analytically that h of a is 0. Because again, think about where h of a is going to be. It's going to land me right on that corner. And we already said, so again, if I wanted h of a, so I plug a in up here, that gives me f of a minus g of a, but we already said that f of a equals g of a. So you could back substitute one in for the other and get like f of a minus f of a, or g of a minus g of a, or ultimately just say, well, okay, 0. And the same would be true for h of b, because it'd be f of b minus g of b, which is also going to be 0. And the graph shows that because it's very easy to say, okay, they're meeting at those endpoints. So that flows us in to backtracking and going backwards to Rolle's theorem. So Rolle's theorem says, is f a continuous function from a to b? So is f a smooth continuous function from a to b? Okay. Is f going to be differentiable everywhere? Okay. Is g a smooth continuous function from a to b? Is g going to be differentiable everywhere? Okay, so then now let's go back to those old properties that says if one function is continuous and differentiable and another function is continuous and differentiable, then I can add, subtract, and multiply them together, and they're still going to be continuous and differentiable. So isn't it fair to say that h of x is always going to be continuous and differentiable? Just think about it. No matter what you do, you're always going to have an f minus a g. So you're always going to have whatever the top is minus the bottom. And they already told you f is always greater than g. So there's no points where I can't take them, except for maybe those concerning endpoints, but the endpoints aren't included in differentiability. So Rolle's hypotheses are met, even to the point saying that my endpoints had to equal each other, and they both equal 0. So, yes, they are, because the hypotheses are going back to the function h, not to f or to g. We're talking about h. So, let's find h prime. So think about if you have one function minus another function. So if I had 2x minus 10 as my g of x, and then my, let's say maybe it was quadratic. So if you had x squared minus 2x minus 10, couldn't you derive that? And you just derive the x squared, you derive the 2x, and you derive the 10 all separately. So it's fair to say then that if I derive h prime of x, its derivative would be f prime of x minus g prime Okay, and then it says, yeah, there's like some more stuff underneath there though. So it says apply Rolle's theorem. So think about Rolle's theorem. Rolle's theorem says that h prime of c has to equal 0. So now I want h prime of c to equal 0, which means I need f prime of c minus g prime of c to equal 0. But what do we know about g prime of c? It's the slope of the secant, right? It's that f of b minus f of a all over b minus a. And this statement right here, because that's where h prime of c equals 0, couldn't I add one of the functions to the other side? Yeah. So I could say f prime of c equals g prime of c.
Isn't that basically f of b equals f of a?
So g prime of c we said is f of b minus f of a all over b minus a. So I get that f prime of c equals f of b minus f of a all over b minus a. This is the mean value theorem. You just proved the mean value theorem. That is like the formal proof of where did it come from. So it does say to sketch on the graph the approximate location of C and the tangent line there. So where would C kind of be in terms of this graph? Remember, we want, yeah, that's what I'm thinking. Like, we want this graph, this f function, to have the same slope as the g function. So I would say like somewhere up on this peak is going to be that c value. So probably like right there. And it's just further left. Like I would approximate my c value to be right in there. Okay, so again, what would be true about the tangent line and the line g of x at this point? Exactly, they're parallel. Yeah, like, exactly, like this, I would just be like, all of this. Because again, that's what you're seeing. You're seeing my two derivatives have the exact same slope at this point C. And that's ultimately leading into that instantaneous rate of change equaling the average rate of change. Because this right here and this are related. Okay, so and I didn't type these for you. These are kind of like me saying, okay, what are the big ideas? What are the big pictures? So the big concluding facts from this is that there can be more than one value of C in any interval. So like in the Rolle's theorem example, we got 2 C's. That's okay. Like there can be multiple. There doesn't have to be, but there can be. Exactly. Okay, the numerical graphical meaning is that x equals c represents the slope of the tangent line equaling the slope of the secant line for both theorems. You just represent them in different ways. And then it's fair to say in the mean value theorem that at x equals c, the instantaneous rate of change of a function is equal to the average rate of change of a function. And what I did was I tried to give you that other, like a real world example. And as I was typing this, I actually thought of another really good one. So again, this is, imagine going on that car trip where your average speed is 60 miles an hour. It's very fair to say that at some point your speedometer is going to read 60 miles an hour. Even if you're in cruise control, your speedometer is going to fluctuate off of that depending on the hills, the curves of the road. So, average rate, instantaneous rate. They eventually meet and match up. And that's what MVT tells you. That's where MVT is going to come into play as we look at bigger examples and more examples. What's another example besides driving? Okay, running. Okay, I was thinking non-moving vehicles or people, like one that even plays a role in our everyday lives, but you don't think about it. Wasn't what I was thinking about, because that's be like a function that changes. Like, think about a function of time and something that's changing. And to change from one thing to another, it has to guarantee itself to hit like another thing. I know, it's so hard to describe what I want. But it affects our lives every day. More so in the winter than in the summer, but every day. Exactly. So like, exactly. So like, they're always going to be like, the high is blah, blah, blah. The low is da-da-da. But in order to be the higher, leave me alone. In order to be the higher or the low, it has to be all the temperatures in between.